Okay, welcome on the lecture on machine learning and bioinformatics. So last week we started clustering. Just to review, for the clustering, we considered only one algorithm, and this was k-means clustering. For that, the goal of the algorithm is to find some representative for the data. Sometimes they are called prototypes or code book vectors, code words, and so on. And the goal of the algorithm is to find such representatives that the difference between the actual observations and the representatives are, or the closest representative are minimal. So the clustering was represented by some vectors B, and B is a Boolean or 0-1 vector, and 1 is BTA if in observation T was assigned to the representative I, so to the ith cluster. The algorithm, I think I need not to repeat, consists in some initial assignment to the clusters, and if we have assignment to the clusters, we can adjust the representative, and the adjusting of the representative means that we move the representative in the middle of the observations, which is done simply by computing mean value from all the observations assigned to the same cluster. So this was assigned to the cluster I. So only for these will this be sub T superscript I be 1, only for observations that belong to the cluster. And here we sum all the observations and we divide it by ones, and 1 is accounted for each observation which was assigned to the cluster I. So this is the mean. So this is adjusting of the means, and the algorithm is iterative. So it continues with new assignment to the clusters by finding the closest representative. The representatives are usually called centroids. So these are the representations for the clusters, and this was an example. We already discussed why the algorithm converges, because the number of different assignments is finite, and we have a guarantee if we change the assignment, we always decrease the criterion, which is here called within cluster diversity. It's actually the sum of squares. Sum of squares of distances between the observation and its representative. So we know that the algorithm converges, and this is actually all. It can produce bad clustering. For example, if some cluster is split it in two clusters by assigning two representative in the set of observations which we supposed to be in one cluster, but it's easy to see if we have multidimensional data. Or we obtain some representative which is far from the data. But because of this computing the representative as the mass center of the or mean of the group of observations, it could happen. And we ended at this point that we don't know what is the proper number of clusters. And here is an artificial example. There were actually 4 clusters which are generated using some two-dimensional normal distribution. And if we select 3 clusters, we obtain at least one representative, which represents two of the original clusters. And we can measure the within cluster diversity as in such a way that for each cluster, we compute the sum of squares of distances between the observations and the centroid, the representative. And this is not in the picture on the left. If we have just 2 clusters, we obtain some high values because it's not enough to use just 2 representative. If he has 3 representative, we have two representative, or respectively the 2 clusters, which have very small within cluster diversity. So this corresponds to this representative below. And the third one represents this cluster, which is much wider. So the sum of squares of distances between the observations and the representative, I mean this representative, will be high. So this is the middle column in the histogram. For four centers, we need not, but we can obtain such a nice assignment for which the within cluster diversity is approximately equal for all clusters, and results for a higher number of clusters we can see down. So how to select the proper number of clusters? So we can try 2 centers, 3 centers, 4 centers, and so on. Next, the algorithm, the outcome of the algorithm is non-deterministic. It depends on the ordering of the samples and also on the initial assignment. So maybe not only on the initial assignment, the ordering is not important. So usually we run the algorithm several times for given k, and out of the runs we can select the run which gives the lowest sum of squares between of the distances between observations and their respective representative. So we can select for given k the best value, so minimal sum of square distances, and then we should select among different k's. How to select the proper value for the k? Within cluster diversity, yes, this could be reasonable, but only in the case if we expect that the clusters are of similar size and similar dispersion. Maybe there are some clusters which are very dense and very small variance, and some clusters which are not so dense. So then, if we insist on similar value for the within cluster diversity, then we will obtain bad recommendation for such clustering. So it strongly depends on the data, and there is no universal method how to say what is the best number of clusters. So usually we try several values for case, and we select one of them. For example, by visualizing the clusters. We have multidimensional data, so we lower the dimensionality into two dimensions and look whether we obtain some clearly separated clusters or not. Or if the data are further labeled, then we can require that the different clusters should be assigned to different classes. There are some method how to measure quality of clustering, and they are usually based on statistics. What is here is just the idea, and don't be afraid. I will explain where are the catches for that. So I have here two archaic information criterion and Schwarz-Bayesian. Oh, Bayesian, so I think this should be a Bayesian information criterion. Both these statistic measures has the same formula. -2 times logarithms of L plus lambda times M, where L is the likelihood. What is likelihood? Likelihood is actually, we would like to measure how likelihood we will observe our set of observations if we assume that there are such clusters. So this is actually just the likelihood. So if we build representation, for example, using this centroids. So if we have such centroid and we obtain some new observation, we find the closest centroid and assign it to the cluster, and then we have set of observations. So we have many such observations assigned to different clusters, of course, and we compute probability that we see such observations. How to compute such probability? This is not easy. This is not easy, and usually we add some further assumptions. For example, we assume that these clusters have some properties. For example, the density of the cluster is highest near the representative, and it vanishes when we go farther from that. For example, similarly like normal distribution. But these are artificial assumptions. Maybe they are not correct about our data. I will return to that. So we need the likelihood of the observation, and lambda and M. Lambda is a constant, and this is actually the only difference between these two information criterions. For the archaic, we use lambda equal 2, and for Schwarz-Bayesian information criterion, we use logarithm n. Capital N is the number of observations. And we would like to minimize such criterion. Here it is applied on this example, and the result is that minimum we obtain for archaic at value 4, and for the Bayesian information criterion also for the number of 4. So both these criterions give us that the best value for k is 4, which is what we would expect. Both these methods depend on computing the likelihood. And usually we assume that each cluster can be represented as multivariate Gaussian distribution. But this is something which is not guaranteed. Okay, I will return to the problem of evaluating quality of clustering later. And if you look in the scikit-learn library, we are working with that in the labs, there are actually around eight criterions for computing quality of clustering. There are actually two groups of criterions. One, when we know the correct assignment. So if we know the correct clustering, and we produce clustering by some method for clustering, we can compare them. And if they return the same clustering as the true clustering, we know what is correct, then the criterion should set, okay, this is the best clustering you could obtain. I don't include several such method, such criterions. I will show just one for these groups of criterions, and it's called a rand index. It's very simple and natural criterion. We actually count the number of pairs. So we pick two observations, and we look whether they were assigned to the same cluster or to the different cluster in the predicted clustering and in the true clustering. True best clustering. So the true clustering is C star and C is the predicted clustering. And we compute the number of pairs which are assigned to the same cluster in the prediction and also in the true clustering, plus B, and B is the number of pairs which were assigned to different clusters in the predicted clustering and different clusters also in the true clustering. So both such types of pairs are correctly predicted. Correctly predicted that they belong to the same cluster or to different cluster. And the number of pairs is the combinatorial number n over 2. So it's n times n minus 1 divided by 2. This is the number of possible pairs. So actually, this criterion says what is the fraction of correctly clustered pairs. And correctly clustered pair is either clustered assigned to different clusters or to the same clusters according to the true clustering. So this value has naturally a range between 0 and 1. And one would expect that low value of rand index. What does it mean if the value of rand index is small? So this means that there is only few pairs that were predicted to belong to the same cluster and really they belong to the same cluster, or predicted to belong to different clusters and really they should belong to different clusters. Anyway, in other words, it's bad clustering. Unfortunately, if we have a completely random assignment, it will not return rand index 0. Such guarantee we do not have. But on the other hand, if the rand index is high, then this means that the number of correctly assigned pairs to the same or to different clusters is high, so the fraction is big. So the predicted clustering is very similar to the true clustering. In order to fight the problem with random clustering, that the random clustering has not rand index 0, there was designed so-called adjusted rand index, denoted here as RIA, which is rand index computed from the formula above, minus expected value for rand index, and divided by maximum possible value of rand index minus expected value. This adjusted rand index has a range of values between -1 and +1, and the random assignment produces approximately 0. Okay, we will not spend much more about it. And I have next criterion, which is applied if we do not know the correct assignment to the clusters. So if we do not know the correct assignment, we can look just at the result and try to say whether according to the assignment to the clusters it's correct or not. And how can we do that? So silhouette coefficient, it's just one of several criterions, so not the only one. We compute the mean distance between a sample and all other points in the cluster. Actually, the value boldface A, this should be computed for each sample, for each observation. So we take one observation and we see that the observation was assigned to some cluster, and we compute mean distance between the sample and all other observations assigned to the same cluster. Similarly, boldface B, this one, is the mean distance between the sample and all the samples which are assigned to the next closest cluster. So for that, we, for example, if the sample is here and this is the closest other cluster, so we compute mean of distances between the observation and all samples in the next different cluster. So the idea is that such distance should be as high as possible, and mean distance within the cluster should be small, because they are close, they should be close together. And the criterion is B minus A divided by maximum of A and B. So these values are computed for all observations, and then we compute this formula. Such formula has a range of values between -1 and +1. What is better, higher value or lower value? Higher value. Higher value means that the next closest cluster is much farther than the observations in the same cluster. So this is better. And actually, this criterion strongly supports convex clusters. So if we have clusters can be of any shape, and if we have two such clusters, then of course the mean distance from the observation to the observations in the same cluster and mean distance to the observations in the closest other cluster are very similar. So these are penalized by such criterion, and if there are such compact or convex clusters, then they obtain usually a higher score according to the silhouette coefficient. As I said, there are several other criterions you can check in the literature or also in the documentation for scikit-learn to compute some criterion of the quality of clustering. Nevertheless, I would like to continue with a different type of clusterings. And k-means we considered for each observation that it must belong to only one cluster. But sometimes we have a situation where some observation could be characterized that it contributes to different classes, and when we don't have the information about the classes, to different clusters. So it's here the text. I will not read it. So the idea is to allow for a given observation to belong to several clusters, and measure or weight how strongly or how much it belongs to a given cluster. We still consider that we have some representatives, like centroids for k-means, and for each observation we will not have just vector like one-hot encoding, which with value 1 corresponding to the index of the cluster to which it should belong, but we have a vector which has sum 1 and can have arbitrary number of non-negative values. And the value in the vector is the measure how strongly it could be assigned to a given cluster. So such assignment is called fuzzy, because there are no crisp boundaries between the clusters. And fuzzy C-means is one of widely used algorithms for computing such clustering. How can we guarantee that any algorithm will converge to some? So for k-means, we have the guarantee that if the centroids are changed, then the sum of square distances between observations and their representative should decrease. So we know that there are several possible paths in the space of possible clusterings. So we can end in different clusterings with different sum of square distances. For the fuzzy means, we will have not this crisp assignment to the clusters, but fuzzy assignment to clusters. Actually, we will not go into any detail. Actually, the convergence can be proved in a very similar way. So if we change the assignment, then some criterion, which is a different criterion, you will see it on the next slide, will decrease. So we have also guaranteed that such algorithm converges to some stable state and which can be considered as the result of such clustering. But how do we decide soft assignments? If we have an observation, how do we decide that it should belong 30% to one cluster, 20% to second cluster, and the rest percent to the third cluster? So this is the idea. So originally for the k-means, we minimized the sum of square distances between observation is xt, and its representative. Mathematically, this was expressed by this vector b, this indicator, which has value 1 for given observation t, xt, only if it was assigned to cluster I, and then the distance, the square of the distance is used in the sum. Only if it is to the distance between the observation and its representative. For fuzzy C-means, we minimize this double sum. So it's also through all the observations and through all centroids. And here we have square distance between the observation and Now I will not say it's representative, because one observation can have several representatives. So to any representatives, but this is multiplied by a vector ht with superscript I, and the vector ht, so it's ht with superscript 1, ht with superscript 2, and so on. And these are the weights, how strongly the observation T is assigned to first cluster, second cluster, and so on. So these are values between 0 and 1. And sum of all these values in the vector ht must be 1. And what is strange for fuzzy C means it has another parameter m. And what is minimized is the weight, the fuzzy weight of belonging, how observation T belongs to cluster I, and it is used their nth power of the. What do you think about this parameter m? Something strange. If m will be equal 1, then it's the same as for the k-means. But still, we have fuzzy assignment to the clusters. So vectors of several possibly several non-zero values. If we increase m, what does it mean? If we increase m, so each element of the vector h is some value between 0 and 1. If we take, let's say, second power square, then we will decrease the value. And how much? If we have some assignment, let's say 0.1, 0.1, 0.8, and the rest of. How it will influence the value 0.1 if we compute the square root, square would be just 1/100, and square of this will be 0.64. So for high value, the decrease is not so high as for low values. So this actually gives higher weight in the criterion, this double sum, higher value for stronger, for crispier assignments, not so fuzzy assignment. Okay, and if we have such an assignment, so such vector, then we can, based on the parameter m, we can compute the same importance of the assignment to the cluster I when we compute the mean for given cluster, and for each observation xt we give its weight, and here in the formula is the weight from the vector h to the nth power. So also here we use the nth power to highlight or to give emphasize of according to the parameter m. So this is the way how to compute the mean. and how to compute the value for the fuzzy assignment for the vector h sub t. So it's here 1 divided by sum, and what we have here, this is the norm or distance between the observation and the centroid. And actually, this distance will be squared, divided by the distance between the observation and some other centroid j. So this centroid I is actually, I am interested how much should I assign the observation t into the cluster I. So I will sum through all possible clusters. Here we have the distance to the centroids for all clusters. This will be still squared, and we take m minus first root from the fraction. And such fractions are summed together. Okay, let us not spend too much time on that. So the idea is that we have fuzzy assignment, and we have some other parameter m, which can emphasize if you would like to have more compact more compact clusters, or we allow more fuzzy clusters. Actually, the value k here is the c from the name of the algorithm. But if you look in the literature, usually we'll see c-means, fuzzy c-means algorithm, not fuzzy k-means. Let us look how it works on some artificial data. So here we have artificial data generated from 4 normal distributions. And normal distributions with centers -1, -1. -1 is here, -1, so it's approximately here. -1, +1, and similarly 1, -1, and 1, 1. So of course, these 4 normal distributions are completely overlapping. I mean standard normal distribution with mean according to the coordinate of the point, the plane, and variance 1, variance, and of course standard deviation 1. So if we use k-means, we obtained such centroids, and if we used fuzzy c-means, also with 4k equal 4, we obtain this centroids. So we can say that this is better approximation for the centers for these 4 normal distributions used for generating the data. And if we compute Akaike and Bayesian information criterion, so this is for the fuzzy c-means, we can similarly find the best value for k, and this is this unreadable 4, and here is also unreadable 4. So 4 is the best number of clusters. Also for such a data where my human eyes don't see any clusters. Similarly, as we have fuzzy c-means, for fuzzy c-means actually assumes that we are looking for the assignment for an observation that the measure for the strength of the assignment depends only on the distance from the centroid. This means that we actually assume that all these clusters are homogeneous in all directions. So roughly speaking, the cluster should be symmetric, and all of them should have the same, let's say, variance. So this within cluster dispersion. But this is usually not true for real data. So in real data, we have sometimes some small clusters, some bigger cluster with different density of observations in the clusters. So for such situation, we can mathematically define a better model based on so-called mixture. What does it mean, mixture? It means that we assume that the clustering is some set of homogeneous clusterings, or in general, a set of different clusters, and for each cluster we can have different model. Different model, this means we assume different dispersion around the representative, and so the clusters can be quite different. Mathematically, it's very easy. We say that probability of observing some vector x is probability of cluster I. So this is the probability for belonging to a cluster without knowing anything about the values in the or elements of the observations, and conditional probability. Probability that if we assume that the observation is from cluster I, what is the probability that we see observation X? And we sum all these probabilities. So formula is quite simple, I suppose. So the capital P of GI, this can be, how can we measure such value? So if we obtain if we obtain clustering, and we know that we have altogether capital N observations, and we have one cluster which contains 100 samples, then the probability of new observation that it will belong to the cluster will be 100 divided by N. Just computing the frequencies. So this is not so hard, and if we suppose that it belongs to given cluster, then if we have some good model for the cluster, for the distribution inside the cluster, we can compute probability that we observe the observation X. And such model is called mixture model because we suppose that we have model for each cluster, and we combine them in one representation, one model for the clustering. Of course, we need model for one cluster, and usually as such model is used Gaussian normal distribution. So we suppose that the probability that we observe X, if we know that it belongs to cluster I, can be described by normal distribution with some mean mu sub I. And what is sigma I? We are in many dimensions. In one dimension, this would be just the variance, but if we have many dimensions, we need covariance metrics. Excellent. So mathematically, it's easy. We just sum k such formulas in which we have normal distribution. how to obtain such model? Of course, I will show just an idea how to obtain that, but for most applications, if we would like to apply that, we say, okay, there is some method. If I say the number of clusters, which will guess the clusters and the parameters for the normal distribution, and after guessing, maybe the guess is not so big, it will improve the guess using some method. If we use the normal distribution for describing the distribution for one cluster, then the distribution can be described by mathematically nice functions. Nice in the sense that are smooth, derivable, and so on. So we can apply some gradient descent method. Actually, we will see that we apply a method which is called expectation maximization, which roughly corresponds to the k-means algorithm. But it's a little more involved. We will not go into any deep detail. I would like you to know that there are some analytical methods like expectation maximization algorithm, which is able to guess and improve, so iteratively improve the quality for the parameters for describing the clusters. And we run such method. After some time, we will stop it and say, okay, what are the clusters? What are the models for the clusters you have found? Okay, so there will follow several slides with many formulas. This is a warning for me. What I would like you to know is this formula what is the model for the clustering, and the idea how it is optimized. But you need not to reproduce the formulas which will follow in few slides here. Don't be afraid, I will not require it from you. So, so in general, the method is that if we can describe the parameters of the model, like a set of parameters, capital phi, then we would like to know whether such parameter, assuming such parameter, what is the probability that we see our observations? Our observations are collected in the matrix capital X. So we have each row is one observation, which is multidimensional vector. And we would like, the method is that we would like to maximize the probability of observing our observations. And we are searching for parameters of the model which maximize such probability. So this is the maximum likelihood estimate. And how can we express such likelihood? So we have probability that we observe one observation. This is described by such formula above. And we have capital N observations. So we must compute probability that we observe all observations together. So actually product of the probabilities. This would be very fast growing to or decreasing to zero. So instead of computing directly the likelihood, we compute log likelihood. So here is the product of the probabilities of observing the observation x sub t under assumption that we have set of parameters capital phi. This is the product, and we compute logarithm of that. So logarithm of the product is sum of logarithms. So this is sum of logarithms, and here is just rewritten the formula from the previous slide for probability of given observation x, or now x sub t. This is not easy. And as I said, the method which is usually applied is called expectation maximization. When we computed the assignment to the clusters for k-means, then we at first we guess to which cluster each observation should be assigned. And after that, if we have such an assignment, we can improve the guess estimate for the centroids. This was in the repeatedly applied in k-means algorithm. And here it is very similar. So at first we guess some hidden variables, capital Z. And when we know such some guess for the variable Z, then we can compute the log likelihood. These are not the most complex formulas you will see today. So in the estimate E step, we estimate the variable Z. What I am showing here is general expectation maximization method applied for computing log likelihood. So we compute some function Q with parameters, our current set of parameters, capital Phi with superscript L. L is a step or iteration of the algorithm. And this is the desired or unknown set of parameters, capital Phi, and we compute this as an expected value of the likelihood. If we know X and Z, likelihood of the set of parameters, capital Phi, based on known set of examples, X, so set of observations, and our current set of parameters, capital Phi with superscript L. And in the next step, we compute the best set of parameters based on the function Q. So we compute maximum of this function. We look at this function as the variable is Phi. It is also the case here. So the Phi with superscript L is our current set of parameters. And both these steps are alternatively evaluated. Also, without any details, if we succeed in increasing the value for Q, then we increase the likelihood that our set of parameters or likelihood that if we obtain if we know that the set of observation capital X, that our set of attributes is better one. So for the fuzzy C-means algorithm, let us return back to our problem. This was general, completely general. In case of mixtures, the hidden variables can be actually the guess for the values of the measure of the assignment to the clusters. We don't know what are there for actually, but this estimate for them can be the measure. The problem is that if we assume that some clusters are dense, some are not so dense, then it's hard to guess the measure, fuzzy measure for assignment for different clusters. So I will leave this, and in each step we estimate these labels, and in M step we then update the centroids. So in each step we calculate such assignment, but in k-means algorithm, the assignment was crisp. We say it belongs to one cluster, the closest centroid. In our case, we for the c-means clustering, this will be values between 0 and 1, and then we re-estimate the centroids. And now is the slide with maybe most variables in this presentation. You need not to reproduce such slide. So I will not ask you to do that in the exam. So don't be afraid. So let us look at that. So if we have crisp assignment, then we can use the value for the z either 0 or 1, zti, and this corresponds to the labels of supervised learning and also to the assignment in k-means. But in case we allow assignment which is not crisp, then these values need not to be 0 and 1, and we need to compute the log likelihood of the of a given set of parameters, capital Phi, if we know x and z. So this is logarithm of product. So this is sum of logarithms. For the logarithms, we just use the formula, and now for this probability, so assuming the parameters capital Phi, what is the probability that we have observed xt and simultaneously assigned the observation to clusters according to vector z. So this will be probability that we have assignment zt based on the parameters for the assignment, and probability of the observation if we know the assignment zt and the set of parameters. Actually, here we use this simple formula. So probability of A and B given C can be computed as probability of B given C times probability of A given B and C. So this is used here. This is logarithm of product. So this can be split logarithm of the first term plus logarithm of the second term. And how to compute that? So for probability of assignment zt based on the set of parameters of the model phi. What are the parameters for the fuzzy C-mean clusterings? This capital Phi. Actually, for each cluster, we have mean, covariance matrix. This is all. And this we have for all clusters. M, yes, parameter M. You are right. You are right. We need it. So, therefore, here we for the probability of zt is a vector. So we can compute the probability of the vector as probability that we observe the first element of the vector, second, and so on. This would be usually product of the probabilities, and our goal is to compute logarithm of the probability. So this will be sum of logarithms. And so it's here. So we have the assignment times the logarithm of probability of belonging to cluster I. And similarly, this is probability of the observation xt. So if we know the parameters for the clusters, we can compute them directly, because this is sum of some prior belonging to the cluster times the conditional probability, which is computed according to the normal distribution. For that, we have a formula if we know parameters for the normal distribution. Still another slide with many formulas. So the function q is the expected value of logarithm of the probability that we have our observations x and all the values z based on the known observations and our current set of parameters, capital phi with superscript I. So this logarithm is the log likelihood, and we can use the formula from the previous slide, and we obtain such a long formula. I will not repeat that, and you need not to remember that. So this is for the E step, and still for this part, there is another slide with explanations how to arrive that, but I will completely skip it. I will not spend time. Similarly, M step is also quite complicated set of formulas. Actually, it's not so complicated. Let us look at the structure at least. So we would like to compute a new set of parameters with superscript L plus 1. And we would like to compute as the maximum expected log likelihood based on our known set of observations, the previous set of parameters, and now we also have estimate for all the values z. And so this is just rewritten from the previous slide, and this is double sum. Here are the expected values. So the expected values can be interpreted as the fuzzy coefficient, or for the clustering, and this is used also here. So these are the expected values. Logarithm of probability. This can be computed just directly if we have assignment to the clusters. And logarithm of probability, it's also easy. So as we have seen, Lagrange multiplier method for solving the problem of principal component analysis. So the same method is used here for optimization, for computing maximum. So we assume that if there is a maximum, then the derivative should be 0. So then we compute the derivative, and out of that we obtain the solution. And the solution, so if we compute these expected values for Z, we obtain the H, and from that we can compute the probability of belonging to cluster I. Of course, we don't have any guarantee that such probabilities, that the sum of HTI is integer. There is no guarantee for that. And then by weighting the observations using the HT, we can compute the means, fuzzy means. So these are the centroids, these are the priors, and what is this? Just guess. Please don't read the formula and guess. This is estimate for the covariance matrix. So for each cluster, we need covariance matrix, and this is the estimate for the covariance matrix. So the resulting formulas are here. Here is the covariance matrix. For that, we compute the approximation denoted as sub I. Okay, so let us go down from the high or complicated mathematical analysis. We use fuzzy assignment to clusters, and we have an algorithm, analytical method, EM, expectation maximization algorithm, which is able to optimize set of parameters. The method is applicable not only when we have description for the clusters using Gaussian. Maybe we have some other method for describing probability distribution around in one cluster. Then we can apply such a method. Of course, the formulas would be different, but the method is the same. So this is a general method how to compute such fuzzy assignment, and the result is set of Gaussians which describe different clusters. Inherently, this means that we have an assumption that each cluster can be described by some Gaussian. If we have such a cluster, this is not possible to describe by Gaussian. So the assumption that we assume the Gaussian model for each cluster is quite strong. For some applications, this could be good assignment. For other applications, this could be completely wrong and misleading. Okay. So in k-means, this is maybe this could be used for describing the differences. For k-means, we assume that each cluster is symmetric in all directions. So actually something like circle in a plane. And fuzzy c-means, we assume that the clusters are described by Gaussians, and what would be Gaussian in 2 dimensions? This would be some ellipse, some ellipsoid. So the clusters can be ellipses of different sizes and different orientation. So this is much more general than just circles. So here is a solution of such an assignment. So here these red observations and some blue observations, and this is described by 2 Gaussians. one with the mean here and second with the mean to the right. Which of these Gaussians has lower dispersion? I mean lower variance. The red one or the blue one? Blue one, of course. What is actually here, this blue ellipse and red ellipse? This is ellipse with the distance of standard deviation from the centroid, but it's hard to say what is the standard deviation in two dimensions. So actually, these ellipses corresponds to distance, to place from the centroid, for which the density is the same, constant. Něco jako v mape vrstevnice. Rovnaká nadmořská výška, tak it's the same here. And actually, it's written here that it corresponds to the fuzzy assignment 1/2. Okay. If we have such a description for the clusters, which consist of different model for different clusters. For the case of Gaussians, we have Gaussian mixtures, and if we know that this is the case, that we can describe them, then we can try to simplify the description. For example, if we suppose that all the clusters should have similar model, similar in the sense that they can have different centers, but similar dispersion around the mean. So such cluster can be an ellipse, and we have several such ellipses, so corresponding to different clusters. Even we could assume that they are rotated, but if we assume that they have the same dispersion, this corresponds to the same covariance matrix. And if we have the same covariance matrix, we can simplify the computation. So if we assume common covariance matrix, then we can easily simplify the computation, and we can no, I will leave it at this. If we further assume that the covariance matrices are diagonal, what does it mean diagonal? This means that the variance in one direction doesn't depend on variance on the second direction. How will look like such Gaussian if we know that the covariance matrix is diagonal? Should it be a regular circle? I mean, these are points for which the density is the same. Could it be of such a form? Or vertical ellipses? Or general ellipses? If we know that the covariance matrix is diagonal. Outside the main diagonal, there are zeros in the covariance matrix. What are the possible shapes? Don't be afraid, you are not an exam. So it can have variance in first coordinate and different variants, for example, smaller in the second coordinate. So this is possible. This is also possible. Of course, a regular circle is also possible, but this is not possible. Because the variance depends. Because the values for the coordinates are dependent. Then it depends on the variance in one coordinate depends on the variance on the second coordinate. So this is not possible. But all such cases are possible. Then we can simplify the computation. But as it is set in the slide, written in the slide, this can remove correlations between the dimensions, and we can lose any information. If this is not correct model for the cluster, for example, the observations are actually spread in such a way, then we obtain something like this, because we assume that the covariance matrix is simple, only diagonal, but this is not the correct model for the cluster. We should end. You should warn me, please. If you know that I am trying to continue after the deadline for the lecture, please let me know. I will be not angry but happy. So okay, I will leave that. Actually, we are almost at the end of this part, and next week we will start with classification, methods for classifying. Thank you very much for your attention, and I will complete that next week.